Professor of Electrical Computer Engineering at the University of Rochester.
Minnesota. Where do I?
There. Undergraduate engineering from the National Technical University Athens in Greece, and then he got his graduate degrees, both master's and PhD from the University of California in Los Angeles. Over the years, he contributed amazing work in several areas that's found in the statistical and processing and learning, communications, and working, for which is post of recognitions, some of which I can cite here that I remember. Is an ethical, he's received the Activities in the Positive Society Top Technical Award, the Society Award, Norbert Wiener Award, also a IEEE Level 3 Award, which is a few award in processing. He's a member of the US National Academy of Inventors, the UK Russian Royal Academy of Engineering, and also the GSP Academy in Athens, with global scope of what is being recognized. In terms of the theme of this workshop, himself and his group have been contributing lots of important work at the intersection of the learning graphs, networks, and beyond, where to describe a few of these spaces, like we call maybe cross-layer design, wireless communication networks, and also spectrum sensing for community radio networks as well, then distributed learning optimization and estimation for wireless sensor networks or network of agents. And as the group transition a bit more network science topics, a lot of contributions as well in terms of social networks, power grids, the renewables, and also even training for economics. But maybe over the last decade, I would say, the group has been focusing on machine learning, AI, learning from graph network data, in a way the contemporary topic of this team, but we've been working on ensemble learning, kernel-based learning, and self-supervised learning. I think that's going to be the topic of this talk today. So it's great to have you here. Our great pleasure. I'm looking forward to hearing more about the exciting research. So please join me in Professor Unitas.
Thank you, Gonzalo, for the kind introduction. I think it's too loud. I need to, it's perfectly fine. Okay. So it's my pleasure to be here at Delft. Thank you so much, Gerd and Elvin, for extending this invitation, and as I said, Gonchi for the kind introduction. So this is a joint work with my postdoctoral researcher, Alireza Salehi, and a recent PhD graduate, Konstantinos Polizos. And at some point, we benefit from some ideas from Professor Mateos that we heard earlier. Okay, let's get started. Oh. It is on. Okay, so that works. Okay. Yeah. So I don't need to motivate graphs for this audience, but it suffices to say that you have two types of graphs. Those that interconnected nodes have physical links, like the power grid in the cable, and those that nodal measurements are correlated. So automatically, you can, if you think of correlation coefficients and they exceed a certain level, you can have an edge. So you can have sort of networks built on similarities. High-level objective of the talk is to infer the values on nodes from a subset of values. So you know some, and you want to figure out the rest, as for example in citation networks. But for several reasons, such as privacy, the cost of label, for example, you may have invented operation, which is very costly. The graphs are large scale, many graphs at large scale, but the number of label data is small. And the reasons are what I have listed over there. Now, this is the motivation. Maybe they admit. I need to admit. Okay. So we talked about the context and the challenges. The novel thing of this talk will be this notion of self-supervision, which has been touched upon in the past, in the recent past, but not as much in the signal processing and graph signal processing community. So I'm going to talk about the abbreviation, which is SESU, self-supervision. I will talk about models and how these models can enable kernel estimates and learning function estimates. Then I will come up with SESU models that are learnable from the data, even online. And I will try to give some performance analysis guidelines using neural target kernels. And numerical tests, and if time allows, I will try to draw connections with transfer learning, meta learning, and so on. Okay, so to set up the analytical exposition, let's start with a graph that has vertices in the calligraphic V. It has nodal vectors, and it has an adjacency matrix A, and possibly nodal feature vectors that build the columns of a matrix X. So you know A and or X. And then you are measuring perhaps noisy values of Y sub n, where epsilon n would capture model dynamics. So the goal now, more concretely, of semi-supervised learning will be that you are given A and or X, and you're observing observations in a subset, calligraphic O for observed, which with cardinality n sub O, which is significantly less than n. That's the setting which is important. And you want to infer everything. So, and for future reference, I want to stress that this AN vector is the nth column of the adjacency, okay? So it comprises spatial graph information to every node, right, the connectivity. Now, xn is your usual nodal vector, so feature vector. And the challenges associated with it, clearly, the moment I show that n sub O is much less than n, you understand that you are underdetermined. You have an underdetermined, if you want to think in terms of solving the system, yn equals f plus epsilon times the masking matrix. The masking matrix, sampling matrix is bad, right? So you have an underdetermined system of equations. So what do we do in signal processing when we have underdeterminacy? We resort to prior information in a Bayesian framework or to regularizers in a Tikhonov regularization approach. At this point, what you want to think is that self-supervision, basically, it is like a form of prior information, okay, that you can utilize to deal with the ill-posed, underdetermined problem. So The issue is, how do we do, what is more complex, to use regularization or to use self-supervision? And then you can keep asking questions like, is the information that is conveyed by the AN, the nth column of the adjacency, is this information enough to do inference? Or you need to resort to XN as well? And what if XN is not available? And to the enthusiasts of graph neural networks, I want to point out that if this X is not available, you cannot run graph neural networks. They're not operational. Yet, you may be able to extract information. Okay? So, since we talked about this graph semi-supervised form and the overdetermined system, this is the goal that I already stated. But now there is one difference. I dropped XN. Okay? I said you're only given AN. Just for brevity in the notation. Later on, I'm going to include the XN as well. Okay? But that stresses the fact that I don't have to have XN. Okay? So, well, how do we proceed whenever we have prior information? You basically designate a space of functions with a specific metric, which is called RKHS for reproducing kernel-driven space, where basically you simply say that my function can be expressed as a linear combination of or superposition or weighted superposition of kernel functions, which you can think of as bases that are sitting on each and every sample AN. And if you've never heard about it and you are in signal processing, just think that sampling theory dictates that any unlimited signal can be expressed as a superposition of sinc functions. So think of a sinc function as a kernel, and then everything would make sense. It is here convenient because it's symmetric and positive definite. But basically, if you formulate this functional optimization problem, where you have a loss function and a regularization, because you are underdetermined, right? Then your optimum function estimate, according to this represented theorem, for a fixed, pre-selected kernel kappa, the solution satisfies this form. But basically, instead of having a large capital N superposition of kernels, you can have an N sub O, which is the number of observed ones. And then you can write this in a product as a vector N sub O by 1 times a set of coefficients alpha. I hope you distinguish alpha with A. And this alpha, you can solve it using an extended regularized Tikhonov type regularizer, and you can basically plug it to find the estimate of the function f. Now, what are the limitations of this approach? First of all, the number of observations, because to solve this regularized system of equations, you notice that you have NO by NO, and you need to invert that matrix, right? Then it's cubic in that size of an O. So the solution, which is very important for us, a very important difference, the solution that I wrote there that represented theorem yields does not take advantage of the unlabeled data. So basically, you form the system of equations using the labeled data. Okay? But you may have an abundance of unlabeled data, and you don't utilize it for the solution. That's a limitation. And this is where the SESU will come to play a role and complement this theory. And then, of course, you can ask what kernel is the best one to use. But once we identify, we can find the estimate of f hat. So this will get me to the notion of self-supervision. Okay. This is a two-box, one input, two output system. So suppose I have on the top box a reference model. It can be a lot of different models, but the important thing is that you know it. You know that the model and you know the output of this box. As an example, suppose that the output is A new, the same as the input. So the SESU model is an identity operator. It takes AN and gives you AN. Okay, but you can have different other functions that you know. So once you know this, what we're going to do is we're going to build another branch, which is a parametric model, and it comprises of two sub-boxes, the compression sub-box, which reduces the dimensionality of the input, and then the decompression or reconstruction box, theta sub D, decoding box. So, and I choose them to be parametric. And from now on, when I say the word embedding, I will refer to this low dimensionality vector rho of A nu. Okay? So why should I bother about these embeddings? Well, here is the major observation. These embeddings, if you think in terms of Mercer's theorem, which basically says that every kernel can be the inner product of two nonlinear maps, P transpose A. Right? Then here, this row of A nus are like approximants of the infinite dimensional. So it's a finite dimensional D. So we are going to see that this estimate of the learning function, which according to representative theorem is the superposition of kappas. If you use, instead of kappa, you use the kappa hat. And this kappa hat is the inner product of the embeddings. Then think of selecting all the functions except the free variable vector A, rho transpose of A, which is of size little d by 1 that you select, times theta. So what did I say here? I said that the moment you use those embeddings, you can view an estimated function as, you can use these embeddings as linear regressors of the model that will yield the estimate of the function. So two things to remember, the embeddings and the SESU are important for two reasons, at least. The first reason is because they can provide low dimensional representation, they can estimate kernels, and they can estimate functions. So, and what I didn't stress enough is the following. The output of the encoder, theta E, can rely on unlabeled data. The A sub nu is unlabeled, can be unlabeled. And then through this unlabeled, I found these two embeddings, okay? I remind you that graphical kernels do not take advantage of the unlabeled, okay? And that's a critical difference here. Now, let me give you two examples so you can digest it, although not so widely applicable. But let's say we take the simplest possible case, which is having the SESU model to be the identity. In the lower branch, I'm going to introduce the familiar spectral decomposition of my covariance matrix of my kernels, which is basically nothing but the matrix involved in getting principal components. Okay? So if the compression is U transpose and the decompression is U, the output of the second box is A hat nu, which is U transpose A nu, which is the low rank decomposition. of the A, okay? So now, if you give me A news, I can train this vector, I can train this and solve with respect to U. I have clearly a D by 1 embedding vector rho of A n. And then the UDs is the tall matrix formed by the D eigenvectors corresponding to the largest D eigenvalues of the matrix. So all I told you is that PCA can provide you this. That's all this framework. That's what I told you. Okay? And then you can ask naturally, why should I confine myself to linear maps? And kernel PCA could do the same. Okay, we can provide you another rho. Now, even more, there is autoencoders nowadays. Okay, what is an autoencoder? Is in my mind is a nonlinear version of PCA. It's trainable, right? So it can. Again, I have a bunch of ANUs, right? So I can train them. Typically, unlabeled data are in abundance. And also, you can have variational or Bayesian approaches of autoencoders that offer additional benefits. I'm not going to get into it. However, although both of these examples provide SESU models that are useful to create embeddings and lower the dimensionality, both of them do not relate to the original task, the original learning task. So when you select which SESU model to use, basically tends to be an ad hoc choice. And in addition to these two that I have up there, examples, there are at least a bunch of other SESU models that people have come up with in recent years. So what is the novelty that we came to put? Why don't we follow the Mercer theorem? And when it comes to the output, try to match the estimated kernel with the original kernel. So if you know the kernel, right, try to select embeddings that will lead you as close as possible to these kernels. It's like optimizing the kernel estimates per se. And basically, once you found the kernel estimate, then you can play the same trick. And now you have reached, now you have linear regression, but with dimensionality D by 1. So what I'm proposing here is a two-level learning. If you give me the ANs and the kernel, then you can learn the embeddings. And then given the data, the observations, and the ANs for the observed data, then in the row, you can learn the theta star. The theta star is just with or without regularization. But all I'm trying to tell you is a principled choice of the SESU model, the self-supervision, is the one that does the best job in approximating the underlying kernel. And if you can do that, and you can approximate the underlying kernel, you will approximate well the underlying function. So we have come up with a SESU model that can take into account the original kernel-based learning function. And then you can start asking, now, how can I select the best performing kernel? Is there a single kernel expressive enough? Well, it's not too difficult to come up with a dictionary of kernels, kappa, p, and then that maps to multiple IK spaces that your function could belong to. And then at the end of the day, you get a linear combination of the estimates from each kernel. And in the right-hand side, you observe that you have a linear function with multiple theta p's. So you have a multi-kernel dictionary that draws from a richer class of functions. So the main task objective is as before, But now the estimation is using multiple kernels. And here is an algorithm that you can come up with. There are many variants, but I thought I will summarize it in one slide. So you start with a known dictionary. You like Gaussian bells, you like quadratic functions, you like RBFs, in other words, or Matern patterns, or different types. You put them all there, and you have labeled data and you have unlabeled data. Using the observed ANs, you initialize the WPs, and acquiring data one by one, node by node, you are proceeding using the SESU model to extract the embeddings corresponding to each and every KP model. Then, given the vectors AN from the observed and the embeddings, you update the main task function parameters. So you see for every, you have parameter theta sub p, that's a gradient descent type of iteration. Pn plus 1 is Pn, and then the cost function could be a loss in the regularizer. And then you can also update the weights. The weights are updated, the parameters are updated in an additive fashion, pretty much like gradient descent, but the other ones are basically between 0 and 1, they are like density functions, right? PMFs. So they are updated with multiplicative iterations, and then you can normalize them. And once you have updated the parameters, you've updated the weights, then you can update the function estimate. And then once you are done and you want to proceed with inference, all your theta parameters are good to go and your embeddings are good to go, okay? A brief exposition on the tests that we have carried out. This is, with kernels in the output, as I mentioned, of the SESU model. And this is different. The one is synthetic to have ground truth, temperature data in the order of 100, and then we'll see something in the order of 1,000. Figure of merit throughout would be the normalized mean square error on the test data from n sub u. U is the unlabeled. So first, we compare the principled, our approach, with kernel PCA and variation and autoencoders. So you see NMSC on the y-axis and the different things on the x-axis. You see that from the left, let's say you have a blue bar indicating the synthetic, how the kernel PCA operates on synthetic data. Autoencoders offer an improvement, but KLSSU basically offers even a better improvement when you match the kernels. And that's, so the bottom line here is what? That the KLSSU has smaller NMSC than autoencoders and kernel PCA for all three data set, and it outperforms the benchmark by an order of magnitude. I don't know whether the y-axis is visible, but you see the axis on the left is 10 to the minus 1, the other is 10 to the minus 2, 10 to the 0 or 10 to the minus 1. Then this is the learnability that we discussed, that you can use. Here we have used 4 different kernels, and that's the K bar, a new that I talked about. And this is, if you focus here again, NMSC over different options, the light blue, or celeste, this bar is the lowest, so it is the best. So that suggests clearly that because when you combine multiple kernels, you improve the performance, and that results in a lower normalized mean square error. And here is coming back to what we discussed. So what is the question? The role of complementing the adjacency matrix information with extra features XN that could be available per node. Okay? Then the answer is straightforward, because when you give me XNs, in particular, I can use the topology identification and build another graph that basically captures the nodal features, right? If, for example, if we have a correlation coefficient between xn, I can have another graph. So I can concatenate the two topology vectors an and xn. So if you look now, again, the NMSC versus different options. Here I'm showing separate kernels, and then the multi-kernel approach is the Celeste one. And if you look at the rightmost, for example, the Celeste one is very small, and likewise for the light green, it's the multi-kernel over different combinations. So when you combine the xn with the an, you have clear improvement. In one case, on the right, for example, if you look the temperature, if you look at the Celeste is the 10, it has only an, and then the 9, which is the light green, it combines the two. So the more information, the merrier. That's basically the message from this slide. So now the issue is how, in this case, an and xn, do we compare with graph neural networks? Because this is basically a thing that one could ask. So if you look at the temperature data, and on the leftmost of the temperature data, I show only the adjacency prior information. Okay, so the Celeste on the right is lower, but not too low. But then the moment you include both an and xn, then the KLSSU, which is the red, goes down 1 or 2 orders of magnitude. Okay, so it improves considerably. And it outperforms also the graph neural network. And we selected 2 of the many that you have options to the graph GCN on the early citation, but the most popular recent years is the simplified GCN. And again, even with that, we have better performance. So the KLSSU lowers the NMSC by an order of magnitude. And if you leverage both unlabeled data to form the KLSSU model, how you outperform graph convolutional models. So I think I have to do now something here. Huh? No? Okay, I think we're good. So let me take a breath to reflect on what are the contributions in context. So in the semi-supervised, we have basically graph priors, but these graph priors that we select do not take into account the unlabeled data. The solution does not take into account the unlabeled data. In the graph neural networks, they require knowledge of xns, right? We don't require any of this. If you look at what people have worked out on self-supervision, they have talked about contrastive learning and masked data modeling and other generative models. I don't know, a very smart one is the masked data model. So you get data, you mask some of them. Think that, for example, this data are your vectors of the adjacency, the columns of the adjacency. So these are links, basically. If you pretend that you don't know, let's say, the link, the entry 3, 5, 7, you keep it aside and you try to predict it. So in your prediction model, then you have, it's like you're trying to solve a graph link learning problem. And then whichever model does the best, that's what you adopt in order to form the embeddings. But again, the problem is that they do not take into account the main learning task at hand. And this is what our principled approach does. Huh? Which one? Okay. So the key contributions are we have a principled approach to self-supervision that leverages unlabeled data that could be abundant. You may know, you may have enough data. And then we can come up with learnable priors using single or multiple kernels and develop adaptive, online, scalable, and learnable systems. So you say, fine, okay, your choice makes sense to go after matching kernels, but they have an analytical support for that. And this is where I was talking with Gonchi on the phone. He says, you know, what you do sounds similar to what people like to call network, neural tangent networks. So, and then we got into it and we found a solution to our performance analysis quest. So it works with a, static regret, so which basically accumulates losses with the online algorithm f hat n, and you use as a benchmark online inference relative to fixed strategy f. So you notice f does not have an n, is fixed in hindsight. And for neural networks, for a neural network with function input a and parameters theta, the neural tangent kernel is basically given by, if you treat theta as a random vector, then on average, it gives you the inner product between the gradient, the sensitivity of your function in the parameter theta. Okay? So that's the definition of the MTK. There are beautiful results that have come up, but for our purpose, the help is, it helped us to come up with the following interesting lemma. I'll try to decode the lemma. That independently we derived, and another gentleman, a bunch of authors did the same thing at 2023 as well. Not in this context. So in this context, basically what we say is that this inner product of the embedding rho transpose rho, which provides a kappa hat, okay? This distance of kappa hat minus kappa, the worst case, because of the soup, right? The worst case error in the kernel is bounded magically by this NTK, the tangent kernel. This was our result. Okay? So if you have a bound on the kernel error, then you can come up with a bound on the function itself. Okay? And that intuitively helps us, along with the two desirable choices. So we choose a loss function that is convex and bounded, and we choose the gradient of it to be bounded as well. If you make those choices, then under these two assumptions, and with the use of the lemma, we can prove that our algorithm attains sublinear regret. N over that width. The width is how many neurons per layer. So you see here that your sublinear N over the width with very high probability. Okay? So that is the take home that Kele is kernel learning, self-supervision, that incurs sublinear regret on average. And we have a numerical test for that. If you plot the regret with all the choices of KLSSU, then across iterations with different kernel choices, you see sublinear regret. And this have also in the network delay in the real data set. So these algorithms indeed attain sublinear regret, which corroborates the analytical results. Let me just touch upon SESU learning over graphs, which could be multiple. That corresponds to generalization of one graph to a multiple, to a network of networks. So the only thing you have to do is to come up with combinations of kernels. So you can have kernels. So you can imagine if you want to decode these graphs, just think of the fact that we belong to LinkedIn and Facebook and what have you, right? Different social. So if you look at every network of friends is this level, then clearly you can have similarities with people within every plane, right? You have friends in Facebook and also across. So if, for example, these layers represent snapshots of a dynamically evolving graph, then you may be correlated in time if this is a sequence of graphs. So whatever, if there are kernels you can construct for continuous variables, like an prime, where an is basically the strength of its link. But also you can have, if you have extra features, you can have different parameters. And you can also have kernels for categorical variables. If you use the indicator function, so you look at two categorical variable vectors, then you can have a summation of entries that are equal to contribute to the sum, and that's a higher similarity between the two. And if you deal with space-time evolutions of graphs, then this kernel, which is a product between a temporal component tau prime, this basically intuitively says that if tau and tau prime are far further away, the two things are not so much related. Okay? It's like the mixing condition in statistics. And then the rest of it. So why do I say all this? There is a field that gets to become very popular that is called Bayesian optimization. And one of the main observations that came out of our group is that we can basically recast resource allocation in networks as basically a solvable problem by Bayesian optimization, just to outline what things look like. So you have cars or Internet of Things that you can come up with, Internet of Vehicles in this case, that can communicate with roadside unit 1, roadside unit 2, and then you want to allocate the resources, like which roadside unit, which base station should I select? That's clearly a categorical variable. And then the question is, with what power should I send? This is an analog value. And such a thing calls for optimizing a function that is energy delay cost, that I'm depicting here as Ft, over a bunch over Z and C. Z is the continuous amplitude, C is the categorical. So you see, I don't want to go into the details, but optimizing this function, because it depends on so many things, prompts not modeling it parametrically, but saying, admit that you don't know and try to estimate the function. Pretty much all I'm trying to tell you is, because the per iteration, this variable, optimization variable x sub t is not available before knowing the function itself, because basically there are many parameters in the link between a unit, a user and a unit that change, and you don't want to track them all. So therefore, you cannot find the function, but you can estimate it in hindsight. So then all the theory that I described with multiple layers becomes very relevant. And this is the average regret, just to demonstrate that indeed you can have exponentially decaying or sublinear regret, I should say, even in a problem that is of interest in communication networks like online and social location, whenever you cannot model the channel, for example, accurately, or you cannot predict what is the load that you want to have your base station to process, and so on. All right, so what are the takeaway points, and what is the road ahead? I thought I introduced this notion of self-supervision. Self-supervision efforts have been out there in the last 4 or 5 years, primarily from the machine learning community. And the motivation is that whenever you have a few labeled data, but abundant unlabeled, then you might as well come up with a sample-efficient learning over graphs. And that one they knew. Actually, in our case, it's very concrete because this lower dimensional embedding, D is the dimension. If you want, I forgot, I don't remember if I stressed it, but if you remember, I said that whenever you have NO observations, we have cubic complexity. Here, you have complexity little d, and the little d you choose. You make it affordable. Okay? And to be sample-efficient learning over graphs. So this was known. What was not known is how to select in a principled way SESU models with embeddings that fit the main task kernels. So basically, if you remember, I talked about kernel-based learning, and I recognized that if I can estimate the kernel well, then I can estimate the function well. So my main task function is well estimated when the embeddings are tailored to match well the main task function. So we talked about learnable models. I touched upon the reduced complexity is OD cube, and I demonstrated that you can have online inference over graphs using self-supervision, how you can have that with gradient descent and the iterations I alluded to. These numerical tests corroborate the SESU merits. And I also touched upon, I provided analytical result for regret and then numerical tests. Now, the road ahead is to talk more about these dynamically evolving graphs and how to take advantage of self-supervision, and also to talk about probabilistic SESU models, because the nice thing about probabilistic SESU models is that you have quantified uncertainty. Pretty much what we're used in signal processing. The moment you provide an estimator, you like to have the variance of it, okay? If not, the distribution to track. So that would be the next step. And self-supervision, I don't know whether you guys are familiar with knowledge distillation. This is a very beautiful name that the machine learning experts have chosen. Basically, they even come up with the term that the top model is the teacher, which is a teacher model. So you basically is a model that you can afford to have as many layers and neurons and as many training data. So in that model, the teacher model. But the student model, which is intended to fit your cell phone, right? Then you cannot afford too many inputs, but parameters that you have learned from the teacher model is the distillation of knowledge that could be utilized for the student model, okay? And this is basically similar to SESU, that can we make that approach principle the way we've made this a principle? That's one question. Then there are basically it's nothing but model reduction. So because even this student-teacher model, you design the student model so that the input-output approach is the teacher as much as possible. So that's all I had to say, and opening the floor for questions. I thank you for your attention.